Okay, let's dive right into this. Welcome to today's Explainer, where we are going to explore a truly fascinating leap in the world of healthcare technology. For years now, we've been trying to teach artificial intelligence to look at medical images and spot diseases. But what if instead of just training an AI to recognize a pattern of pixels, we could actually give it a doctor's imagination? Today, we're unpacking a groundbreaking piece of research that proposes exactly that. It's a framework called MEDVCR. And honestly, this isn't just about better data processing. It's about fundamentally changing how machines think. We're talking about giving them the ability to reason, deduce, and literally imagine alternate realities to make far more accurate medical diagnoses from clinical videos. So here's our roadmap for today. We'll start with the AI diagnostic gap, then move into thinking like a doctor. From there, we'll unpack the MEDVCR framework, followed by learning the clinical rules. Finally, we'll dive into testing the AI results and wrap the whole thing up with the future of diagnosis. All right, part one, the AI diagnostic gap. To really appreciate this new technology, we first need to understand exactly why current state-of-the-art AI models, what we call spatial-temporal models, are falling so short when it comes to clinical video analysis. I want you to really think about this for a second. How do human doctors actually diagnose cancer from a clinical video? Think about a colonoscopy or a cervical exam. A doctor isn't just staring at a static image, blindly matching the exact colors they see to some textbook picture. Not at all. They're playing detective. They're actively hunting for clues over time, watching how tissues react to different tools or chemical reagents as the video plays out. They're actively processing what's happening, rather than just acting like a machine that statically matches pixels on a screen. Just look at the stark contrast we have here. Over on the left, we've got previous AI methods relying on what's called pixel mapping. They are purely data-driven. They look at visual changes across frames and try to map them directly to a diagnostic output. The huge problem with that? They get easily confused. A camera moves, the lighting shifts slightly, or maybe a medical fluid is a certain color, and suddenly the AI is completely thrown off. It conflates those normal, non-pathological variations with actual disease. But then, on the right, we see true expert reasoning. Human doctors are hypothesis-driven. They mentally simulate alternatives in real time. They ask themselves, well, what if this tissue were healthy? Or what if this were actually malignant? By mentally contrasting the actual observation against a hypothetical scenario, they separate the true disease from all that background noise. And that imaginative reasoning, that is exactly what current AI has completely lacked up until now. Which brings us to section 2. Thinking like a doctor. If we want AI to stop getting tricked by something as simple as camera glare, we need it to adopt an entirely new paradigm. The technical term for this new approach is counterfactual reasoning. Sounds a bit sci-fi, but as defined here, it's simply the mental simulation of alternative realities. It's comparing what is actually observed right in front of you against a hypothetical scenario. It is the AI literally asking itself, okay, what if this tissue were healthy instead of malignant? By forcing the AI to generate and analyze that what-if scenario, it learns to isolate the actual generalizable diagnostic clues. It stops getting distracted by sparse data or random incidental visual correlations. Now, what's really interesting about this graphic is how it visually breaks down that shift. Up top, in section A, we have the old way. An input video goes in, data processing happens, and a diagnosis comes out. It's very linear, very rigid. But drop down to section B, the MEDVCR approach. The video goes in, but look at the film strip right below it. The AI looks at the current stage of the tissue and then uses a counterfactual generator to literally picture a healthy next stage in its mind. It generates this smooth, uniform image of what the tissue should look like if absolutely nothing was wrong. Then it compares that imagined healthy tissue against the yellow, rough, actual next stage. The AI is essentially playing a high-stakes game of spot the difference between reality and its own imagination, and that leads to a vastly more robust diagnosis. Moving right along to section 3, the MEDVCR framework. So, how exactly do you build a machine that can imagine alternate realities? Let's take a look at the actual blueprint. The researchers built this architecture using 3 distinct interconnected components. Step 1 is the Counterfactual Generator, or CG, which handles the actual imagining part. Step 2 is Counterfactual Representation Learning, or CRL. That's what teaches the AI to extract meaningful features by comparing those real and imagined videos. And finally, step 3 is Dual Diagnostic Prediction, or DDP, which makes the final medical call. Let's walk through this entire pipeline step by step. Over on the far left, you have your standard input video. Notice how the counterfactual generator takes a frame, adds noise to it, and uses a diffusion model, yeah, actually very similar to the tech behind those wild AI art generators you've seen online, to synthesize an alternate tissue transition. It's generating the counterfactual right there. Then in the middle section, both the real video and the AI-generated alternate video are fed into the visual encoder and temporal transformer. This is the representation learning phase, where the system extracts the core spatiotemporal data. Finally, on the right, the dual diagnostic prediction head takes the global context of the whole video and combines it with a frame-by-frame contrast between the factual reality and the counterfactual scenario. By suppressing cues that align with the wrong hypothesis and boosting the cues that align with the true pathology, it outputs highly reliable diagnostic probabilities. It's pretty brilliant. Okay, Section 4, learning the clinical rules. Because let's be honest, if you give an AI an art generator's brain and just ask it to imagine things, it might just make up wild, physically impossible scenarios. We absolutely need guardrails here. So the crucial point is that this AI is heavily constrained by explicit, real-world clinical knowledge. During that middle learning phase, the researchers enforce 3 strict rules. Rule 1 is temporal consistency. This simply tells the AI that disease doesn't just magically pop in and out of existence between video frames. The pathological status remains stable, even if the lighting completely changes. Rule 2 is pathological separability. This forces the AI's internal math to keep benign and malignant signatures distinctly separate because they arise from different biological processes and literally must look different. And Rule 3 is counterfactual alignment. This ensures the AI's final diagnosis actually aligns with the true state of the observation, while it actively rejects any incompatible alternative assumptions. These 3 rules ground this incredible imaginative tech in hard factual biology. To see why those rules matter so much, take a look at this real-world application in colposcopy, which is a procedure used for cervical cancer screening. The doctor applies different reagents to the tissue. On the left, acetic acid has been applied. In the middle, iodine has been applied. Notice how drastically the tissue's color and texture change from frame to frame. It goes from a pale pink to a deep dark brown, revealing these transient yellow, rough patches. The AI has to track these very specific temporary reactions across time to identify the red biopsy sites on the far right. Because of Rule 1, temporal consistency, the AI knows it's looking at the exact same tissue condition despite those massive color shifts caused by the chemicals. It tracks the true pathology instead of just getting confused by the sudden appearance of dark iodine. All right, Section 5, testing the AI, results. Theory and cool architecture diagrams are wonderful, but does this detective method actually work when put to the test? The researchers tested this out on a fully supervised colposcopy dataset to see just how well the AI could localize actual biopsy sites. And the results? They are striking. General video AI models, like Timesformer there at the top, struggled heavily. They scored only 70.4%. Specialized medical AI models, like SearchFormer, definitely performed better, reaching 82.8%, but MEDVCR, utilizing this brand new counterfactual reasoning, absolutely crushed the previous state-of-the-art baselines. It achieved a staggering 93.0% on the recall at 1 metric. That means it was incredibly accurate at identifying the exact correct regions for a real-world biopsy. And this brilliantly illustrates that it wasn't just a fluke on one highly detailed dataset. Take a look at this colonoscopy test. This was in a weekly supervised setting, where the AI was tasked with detecting polyp frames. Now, weekly supervised means the AI had far less detailed labeling to learn from. We're talking just general video-level tags rather than explicit frame-by-frame annotations. Even in this data-scarce environment, looking at an entirely different type of clinical video, MEDVCR still reigns supreme. It hit a massive 94.8% average precision, completely outperforming the absolute best medical AI baselines, like 𝗏𝗏 I literally just have to pause on this number right here. A plus 10.2% jump. That was the improvement MEDVCR showed over the absolute best previous model in the colposcopy test. Look, in the world of healthcare AI, improvements are usually measured in tiny fractions of a percent. People fight tooth and nail for 0.5%. So a 10.2% leap, that is monumental. It proves that teaching an AI to reason through what-ifs isn't just some neat academic trick, it is undeniably a vastly superior way to process complex clinical data. Which brings us to our final part, Section 6, the future of diagnosis. What does this massive leap in capability actually mean for the medical field moving forward?
The researchers summed up their study with this really powerful statement. We anticipate that this counterfactual reasoning paradigm will open new avenues for vision-based clinical diagnostic tasks toward more transparent and interpretable decision support. And that right there highlights a massive, highly practical benefit we haven't even touched on yet: interpretability. Because the AI is literally generating an image of its what-if scenario, a human doctor can look at that generated image and understand exactly why the AI made its decision. The model stops being a mysterious, frustrating black box. The AI is actually showing its work, and that allows human physicians to genuinely trust the decision support it's providing.
So I want to leave you with this to chew on. We've just seen how giving an AI the power to imagine alternate realities can create a 10% jump in accuracy for something as critical as cancer screening. If models like MEDVCR can successfully play the role of the medical detective in colonoscopies and cervical exams, how is this kind of imaginative AI going to revolutionize other complex fields of medicine? Could it simulate incredibly complex surgical outcomes in real time? Could it precisely predict a disease's progression before the symptoms even visually appear? The paradigm has absolutely shifted, and the possibilities here are truly endless. Keep exploring, keep learning, and thank you so much for joining me for this explainer.